Okay, we'll solve some more problem related with design of flanged beam section. Let me write the problem. The problem is in a normal T-beam slab construction, the beam are spaced at 3 meters center to center. So we'll draw the sketch and then it becomes very clear, but it's been given that you have a normal T-beam slab construction, that is beam and slab has been casted monolithically, and adequate amount of reinforcement of slab is embedding into the beam also. Okay, so that is why it is written T-beam slab construction, and it's also given that these beams are spaced at 3 meter center to center and is simply supported on 6 meter span. The characteristics load supported on 120 mm thick slab are 6 plus 4 kilonewton per meter square, being a combination of dead load and live load respectively. So here the 6 is the dead load and 4 is the live load on the slab. In addition to the loads from the slab, say an intermediate beam supports a wall load of 12 kilonewton per meter and its surface. We'll come to this problem when I draw the sketch, then it becomes very clear. So we have to design the beam for flexure, but we'll see for the same problem once we learn about designing for shear. We can do the shear design, that is stirrup, and also we'll make a check, that is check for deflection. So that also we'll be doing, but we'll do it in the later stage when we learn those topics. But right now you have to just compute the design part from the flexural perspective. So the materials which you have to use is use M20 grade concrete and Fe415. And here I'm going to give you some variation. I'm going to ask you that determine the location 30% to 50% reinforcement can be theoretically curtailed. By curtailed, I mean to say that you can cut the reinforcing bar at some specific location where the applied moment is actually very less than the moment of resistance. So at that point of or at that particular section, you may not require that amount of steel. So you can actually reduce it by curtailing it, that is, you can cut it. So we'll talk about this when we discuss this problem. So first, what is this problem about? So we have to design a beam which is being spaced at 3 meter to center to center. So what you do, you imagine, say this is one of the wall which is running in this direction, and there is another wall which is running in this direction. Okay, so this is continuous. Now what you are giving? You are giving a slab. Okay, in this wall. So in order to give this slab, what you are doing, you are placing a beam here. So you are placing one beam over here, another beam over here. So like this you are placing these beams. So these are beams. These beam lines are beams which is being spaced at 3 meters center to center. Okay, by 3 meters center to center, I mean to say that here the center line of the beam. So this distance is 3 meter. This distance is 3 meter. It is like this. So this is the problem which has been given, and also it has been said that at any one of the intermediate beams, say this is the intermediate beam. So over this intermediate beam, say this on this beam, say you have a wall which is carrying a load of 12 kilonewton per meter. So obviously this beam is going to have more load compared to the other beam, and if I can design this beam, same beam detailing I can give to this beam, and other beams which is going to support the slab which is spanning across this wall. Okay, so let's calculate what is the load for which this beam will be designed. Also here it's given that it is spanning on 6 meter. Okay, it is spanning on 6 meter. So the span is 6 meter. So this beam is having a span of 6 meter. So to start with, I need to know what is the width of the beam which you should provide and what should be the depth of the beam you should provide, because there is nothing which has been mentioned. So first step, what I'll do is step 1. I would like to decide the trial cross section. Okay. So what should be the trial cross section of the beam? That is, what should be the width of the web of the beam, because it is a T section, and also I should know what is the overall depth of the beam. What is the overall depth of the beam, and later, depending upon the cover and reinforcement which you are providing, from there you would be able to know the effective depth. Okay. So how to start with? Like if I see this beam, any beam, say this is of span L. Say this is a simply supported beam. It is having load W. I want to reduce this maximum deflection of the beam. How I can reduce it? What is delta max for this case? It is going to be 5 WL to the power of 4 by 384 E. What I should do such that my maximum deflection is going to be less. Here you see W is given, L is given, the E is given. I, the cross section, has to be such that it gives you little deflection. So what you should do?
So moment of inertia.
Moment of inertia, of course, moment of inertia. So say if you have a rectangular section, please see here, you know for a rectangular section, you have I equal to BD cubed by 12. So rather than changing B, it is always good to go for change in the dimension of D. So more the depth of the beam, you will be getting less deflection. And in code also it is given, because I'll be talking about this thing when we talk about deflection control. But I'm introducing this right now because I need to select this trial dimension as I've written here, trial cross section. With what trial cross section I should start with. So it gives me some indication that there is something related to what this effective span by D ratio. Okay, so your span to depth ratio is going to govern the deflection control actually. Okay, because you can see here D is one of the factor which controls the deflection, and more the span, more the deflection is, because here you see L to the power of 4. So if I increase my length of the span slightly, my maximum deflection also changes. Okay, you get some kind of intuition. I can control my deflection with reference to my span to depth ratio, and it is there in the code, but right now I'll not be using that provision. Here you can see clause number 23.2.1. So in this clause, which is there in page number 37, it is written the vertical deflection limits may generally be assumed to be satisfied, provided that the span to depth ratio are not greater than the value obtained as below. So we have a simply supported beam. So it means that span to effective depth ratio for span up to 10 meter. And what is the span of the beam? We have a 6 meter beam. So I should make sure that my span to effective depth ratio of the problem should not be more than 20. Okay, but this 20, whatever it is specifying, this gets modified. It gets modified based upon amount of tension reinforcement or compression reinforcement, or based on flange action. This gets modified. So these things has been mentioned over here. If you read point number C, point number D, and even point number E, I will be using this when I do the provision for deflection check, when we explore that chapter on controlling deflection in the beam. So there I'll be looking into this provision. But right now, just for a guideline, okay, this was just an introduction how to get into the trial depth of the beam. But rather than that trial depth, to start with, what you can do is generally, so this is just a guideline, this is a thumb rule. You can start with any depth, but later what you have to do, you have to satisfy the strength requirement, deflection check requirement. But to start with, it's just a guideline. The depth of beam may be L by 12 to L by 10. Okay, so this is just a guideline for you. Okay, but if you are not very much convinced with this guideline, what I can suggest, you can take your L by D equal to 20. So from here, what you can see, your effective depth D will be 6000 divided by 20, which is going to be 300 mm. So you can start your trial dimension with effective depth D equal to 300. So you can start with this. But later what you will find that you have to revise this calculation based on those check requirements. Because finally you have to do the flexural reinforcement calculation, you have to do shear reinforcement calculation, then deflection check also. So rather than this initial procedure, I'm giving you this guideline which will always satisfy your design. And if you want to do the economical design, you can always reduce the depth of the beam. So I'm asking you to provide the depth of the beam in the range of L by 12 to L by 10. That is 6000 divided by 12 is 500 to 600 mm. Between 500 to 600 mm, you can go for the depth. Now what I will do, if you see the T-beam, it looks like this. This is your thickness of flange or thickness of slab. Thickness of slab given is 120 mm. Now this is the depth of your rib. So this is the depth of rib. So overall, you can adopt this thickness as between 500 to 600. Say if I adopt this depth of rib as 450 mm, your overall depth of the beam, this becomes 450 plus 120, which is 570 millimeter. So this is the trial thickness with which I am starting, 570 millimeter. And we do not know what width we should adopt. So in general, what I will suggest, so whatever is the thickness of the wall, for aesthetic view, you would like to restrict the width of the beam equal to the width of the wall. So assuming the width of the wall as 230 mm, I'll adopt the width of web. Okay, so I'll adopt width of web BW equal to 230 millimeter. So someone of you can go with this dimension also. You can say the overall depth of the beam. So someone can try this. You say that you are going to provide overall depth of the beam as 500 mm, and someone can say that I'm going to provide width of web as 250. So you can go with this design also. Okay, so there is no hard and fast rule that I have to stick to this dimension. You can vary your design cross section. So you can try with this 500 mm or 250 mm and see what is the changes. And someone can go with 650 mm depth also and go with 250 mm thickness of web and see how the change occurs in your design and in the design which I'll be doing. So my trial cross section is being done. Now next what I will do, my step number 2 is going to be my load calculation. Whatever is the load which is going to be there in this slab, it is going to get transferred to this beam. So how you can actually compute the load? So if I see this area, half of the load from this area is going to transfer its load to this beam. Okay, considering one-way load distribution. Similarly, from this area, half of this slab portion load will get transferred to this beam. So I can see that my contributory area will be this part. So this is the contribution which I'm going to have. So this entire area is going to contribute the load to this beam. So what you are doing, you are considering half of this span. So half of this span is 1.5 meter. Similarly, half of this span. So this is 1.5 meter. So total area of the load which is contributing load to this beam is going to be 3 by 6 meter. Okay. Suppose if this span would have been different, if this span would have been 4 meter. So here you would have used 2 rather than 1.5. So you have to understand half of that particular span you have to consider when you actually compute the load contribution from the slab to the beam. So I have done half of the span from the one part and half of the span from the other part. So this is 3. Okay, so what I'm going to do is so load calculation. So first I'll do what is the load from slab. What is the load which is going to come from the slab? So in this slab, what was the load? It was given 6 plus 4. Okay, 6 is the dead load, 4 is your live load. What I can do, what is the total dead load which is acting on the beam from the slab? So I can multiply 6 into 3 into 6. This I can do. So let me do that. Load from the slab. So first I'll do dead load. So I am having the load magnitude as 6 kilonewton per meter square. Okay, into 3 into what is the span of the beam? This L I'm talking about. This L. If you see this unit, this is in kilonewton, but I would like to know what is the load in terms of kilonewton per meter. So I'll divide this by L. So this L cancel out. So instead of multiplying L, I can directly write 6 into 3, which is going to give me 18 kilonewton per meter. Similarly, live load, what I can do, it was 4. So I can multiply with 4 into the contributory width. So contributory width is 1.5 plus 1.5, which is 3. So I can do this 4 into 3, which will give me 12 kilonewton per meter. All right. Next, in this intermediate beam, apart from this dead load and live load, you have additional load of how much? If you see, 12 kilonewton per meter. Okay, so it is going to support 12 kilonewton per meter load and its self weight. So first is wall load, which is again 12 kilonewton per meter. Next is the self weight of beam. So how you are going to compute the self weight of the beam? Here, this 120 mm thick slab are being combination of dead load. So already 6 kilonewton per meter square. The self weight of the slab has been given to you. Okay, but here I want to know what is the self weight contribution from the rib part. That is this one, because this is forming the slab part. So that dead load is already been included. But what I want, what is the dead load contribution from this shaded part, rib part? So rib part is 450 mm deep and 230 mm wide. So this is 230. So for RCC design, RC work, the density of concrete is 25 kilonewton per meter. So please make this. For RC work, the density of reinforced concrete is 25 kilonewton per meter. So what is going to be the self weight of the beam? Density into cross section. So cross section is what? That shaded portion which I had made. 450 deep into 230 mm. So I am going to multiply this 25 into 0.45 into 0.23. So this will give me in terms of kilonewton per meter. So how much it is coming?
2.59.
2.59. So you can see I have computed what is the load actually going to act on your beam. One is from slab, one is the wall load, which is going to be supported directly on the beam. Next is the self weight of the beam. So here I'm rather than beam, let me write it down, self weight of rib. Okay, the rib portion. So it is 2.59 kilometer per meter. So what is the total load which is present in the beam? Add all the load, 18 plus 12, 30, 42. So it is coming how much? 44.59. So total load is 44.59 kilonewton per meter. So this is the load for which you have to design this beam, because this is the service load. So this is the service load for which you have to design the beam. Since I will be adopting limit state design, and for limit state design we consider factored load. So what is going to be the factored load? Whatever load we have, it is dead load and live load, and we know the load factor for dead load and live load. It is 1.5. And suppose if you are a little bit dubious about it. So I suggest I'll show you this provision which is there in the code. Okay, here it is. Value of partial safety factor gamma f for loads. So you can see dead load plus imposed load. What is the load factor? 1.5. And what it is? Limit state of collapse. So whenever you are using dead load plus imposed load, the load factor is going to be 1.5. But if you have dead load plus imposed load is your live load plus wind load or earthquake load, then you will consider the load factor as 1.2. But in my case, only I have dead load and live load, so my load factor is going to be 1.5. You multiply 1.5 into 44.59. So what is the factored load for which you'll be designing the beam?
66.89.
Okay, 66.89, say 67 kilonewton per meter. So I'm designing for a little bit more load, so I don't have any problem with that. So it is nearly equal to 67 kilonewton per meter. What will be the reaction? So please understand, you have the problem like this now. You have a simply supported beam. The load which is acting on this beam is 67 kilonewton per meter, and you have a span of 6 meters. So what is going to be the maximum moment for which you'll be designing your flexural reinforcement? So ultimate maximum moment. So it will be WUL square by 8. So I can directly write it down 67 into 6 square by 8. Because I hope you remember, if I see the bending moment diagram for this loading, it looks like this. So this is the bending moment diagram. And here whatever moment you are going to get, this is the maximum, which is occurring at the mid span. So if this load is WU, so the moment will be WU into L square by 8. So for this moment, or this maximum moment, you would like to design your reinforcement. So what is this maximum moment?
301.5.
301.5 kilonewton meter. So I highlight this. Similarly, you also compute what is the reaction or what is the shear force for which you'll be designing the shear reinforcement later in one of the class. When we finish this shear concept, we will design the shear reinforcement for the same problem. So that is why what I will do, I will calculate the shear force. So how the shear force distribution looks like for this beam? It will be maximum near support. It will look like this. So this is your bending moment diagram. This is your shear force diagram. And from shear force diagram, you can see maximum shear acts near support. So what will be VU? It will be 67 into 6 by 2. That is the reaction.
201.
201. Since we have to design only for flexure, I will focus for designing with respect to this beam. So the problem could have been given for you directly, like design a T-beam where the ultimate moment applied is 301.5 kilonewton meter. So here you see the difference. Here we have actually derived this 301.5 kilonewton meter based on the data which was given to us. Okay. So the next step, so I have got the load calculation. So next step is to compute the reinforcement. Okay, so let me write down step 3 where I'll be doing further step calculation of reinforcement. So this calculation of reinforcement will require some data. What is the effective width of the flange? Okay, so I need to know what is the effective width of the flange. So effective width of the flange, so I assume you know how to compute it. So it is there in the code, which is L0 by 6 plus 6 times depth of flange plus width of web. But let me show you where exactly it is given. Okay, here you can see page number 37. For T beams, effective width of flange is L0 by 6 plus width of web plus 6 times depth of flange. Okay, so this is given to you. So I can compute the effective width of flange L0 by 6 plus 6 times depth of flange plus width of web. So what is L0? It is the span of the beam because it's simply supported. Okay, so in simply supported, both end point moment is going to be 0, so that itself will be L naught. By 6 plus 6 times depth of flange was 120 and width of web which you have adopted is 230 mm. So based on this, how much is the effective width of the flange? What is the effective width of flange?
1950.
How much? 1950
50.
millimeter. So this is the effective width of the. Okay. Now I'll be requiring the effective depth D. Okay. So adopting. So what should be the clear cover to the reinforcement which you should give? So it depends upon the exposure condition. So again, I will show you all those provisions. Though I can write it directly, but you should know from where exactly you should take your data. Okay, here you can see. Yeah, you can see. You have mild exposure condition, moderate exposure condition, severe. Now, this beam is going to be within a room, so you will not be having moderate, severe, or very severe or extreme exposure condition. So the exposure condition which you can see is mild, which can be 20. Now, based on the firefighting resistance also, you have a beam simply supported. If you want a fire resistance of 1.5 hour, you can see the code is specifying 20. So based on this, I am adopting clear cover, adopting a clear cover of 20 mm, and I do not know what diameter of the bar I'm going to use, but say say 20 mm dia bar is adopted as main reinforcement. Why I need this to compute the effective cover. So if I adopt this, if I see this cross section, this is, I'm saying that I'm going to use this as 28 dia bar. Okay, so this from here till here, this is 20 mm, and from here till here, you have this as 10 mm. So what is going to be effective depth D? So effective depth D is going to be, so the overall depth of the beam was 570, I guess. Okay, 570 minus clear cover is 20 mm minus diameter of bar divided by 2. So 20 divided by 2. So this 20 is your clear cover and this 20 is your diameter of the bar. So if I do this calculation, I get 540 millimeter. So you have D as 540 millimeter. Now, how to design my flexural reinforcement? If you have watched that video, how exactly we used to do. So I had asked you to compute what is mu at depth of flange. First you compute this. What is your ultimate moment of resistance? Okay, when your neutral axis lies in the depth of flange. So that you can do. So the formula which you used to use is what? 0.36 FCK width of flange into df into d minus 0.42. How much this is coming? So how much this is coming? Substitute all the values. 0.36, grade of confidence 20. Effective width of flange we have computed 1950. This is 120. D is 540 minus 0.42.
824.88.
824.88 kilonewton. So there is a purpose of calculating this. So you can see the applied ultimate moment is going to be 301.5 kilonewton meter, and what you are getting, the moment of resistance for neutral axis to be exactly at the depth of flange, there you are getting what 824.88. So by comparing these two moments, you can interpret that your neutral axis is lying within flange. Okay, with this logic, I can write, since the design moment or mu max for which you are going to design your reinforcement is less than mu df, neutral axis lies within flange. So I want to know whether I have to design a singly reinforced section or a doubly reinforced section. So in order to know whether to go for a singly reinforced section design or doubly reinforced section design, you have to compute limiting moment of resistance corresponding to what when neutral axis lies within flange. Okay, so we have to understand, you have to compute limiting moment of resistance corresponding to the case when neutral axis lies within flange. So again, in that video, I have shown you how to compute your limiting moment of resistance. So I can write here the formula directly: FCK width of flange into XULIN into D minus 0.42. So I can use this directly. So for Fe415 steel, you know XULIN by D is 0.48. So from here, what you can do, you can compute XULIN. So XULIN is going to be 0.48 into D, which is 540. And what you do, you substitute this XULIN value over here and give me the value of MULIN.
1568.96.
1568.96 kilonewton meter. So you can see, since mu max is less than MULIN, design singly reinforced. So you can see, since your mu max is less than MULIN, you can design a singly reinforced section. So now what you can do, you can compute your AST. So how you can compute your AST? It's quite simple. If you want to do it a little bit fast, you can use this formula directly, which I had given you. If you recall, to compute the percentage tension reinforcement, I had given you one formula. So if you want, you can write this formula directly. PT equal to, this is percentage tension reinforcement, okay? Percentage tension reinforcement 50. You can remember this formula because this is very handy. 1 minus square root of 1 minus 4.6 FCK mu by BD square divided by Fy by. So please remember this formula. Whenever you have a singly reinforced section, apply this formula. Okay. Now, what you will be doing here, instead of B, substitute with effective width of flange in this formula. Okay, in this formula, when you are substituting, you substitute B as effective width of flange, and now you give me what is the percentage tension reinforcement. And suppose if you are not remembering this, I'll give you other way also. You come to an axial regime. Okay, you come to an axial regime. What this is saying? It is saying for XU less than depth of flange, the moment of resistance may be calculated. You use this formula. So G1.1, I'll come to G1.1. And you see this mu equal to 0.87 FIASTD. In this formula, you substitute mu equal to mu max and B with effective width of flange. You'll get a quadratic equation. Solve that quadratic equation and you get AST. Okay, but here whatever I have given, I given percentage tension reinforcement. What do you mean by percentage tension reinforcement? This is 100 AST by. So this percentage tension reinforcement is 100 AST by BD. So this 100 AST BD by 100 AST by BD is given by this formula. And purposefully I have given you this because I would like to show you a provision in the code which says that you have to provide minimum this much amount of tension reinforcement. Minimum tension reinforcement has to be provided in a beam. So I need to make sure that whatever percentage tension reinforcement you are getting, that should be actually greater than that much percentage of tension reinforcement which is specified in the code. So make this note, percentage tension reinforcement is 100 AST by BD, and this is the formula. Can you please tell me what is the percentage tension reinforcement which you get to resist the maximum moment? So this MU is your maximum moment which is actually acting in the beam for which flexural moment has to be designed. So percentage tension reinforcement is 0.29 and it is actually greater than minimum steel which has to be provided in the beam. So let me show you from where you are going to get this AST minimum. So it is coming from this. So please see clause number 26.5.1.1 tension reinforcement. Minimum reinforcement is writing the minimum area of tension reinforcement shall not be less than that AST by BD equal to 0.85 Fy. Okay, so AST minimum is given as what? AST by BD, okay, equal to 0.85 by F. So there are sometimes question which is being asked for Fe415 steel. What is the minimum percentage reinforcement in beam? Okay, so it is possible it may be asked what is the minimum percentage tension reinforcement for beam for Fe415 steel. So you do 100 AST by BD. So this is your percentage tension reinforcement. So you do 100 into 0.85 by Fy and do this calculation. It will be 85 divided by 415. So how much it is? 85 divided by 415.
0.2048.
Okay, 0.20. So for Fe415 steel in a beam, you have to make sure that minimum percentage tension reinforcement has to be 0.2. Now what you are getting? You are getting 0.29, which is greater than 0.2 percentage. Okay, so this 0.29 is actually greater than 0.2 percentage. Okay, so this AST minimum, I'll write down the clause for your reference. It's there in page number 46. Okay. So you can compute AST minimum from page 46, clause number 26.5.1.2. Okay, so from here you can actually compute AST minimum. But I have modified a little bit. It's like for Fe415 steel, you can remember minimum percentage tension reinforcement is 0.2 percentage. Similarly, what is for Fe500 steel? You'll be doing 85 divided by 500. So this is minimum, okay? How much is coming?
0.17.
0.1. So you can remember these values. This is always good. And you can remember what is the minimum tension reinforcement for beam? 85 divided by Fy. So that will be in terms of percentage tension reinforcement. Then I suggested you to use this formula, which is applicable. So please note this formula is applicable when your XU is less than depth of flange, or you can say when neutral axis lies within flange. So make this note. So this standard formula which I have written over here, this is applicable when your neutral axis is going to lie within flange. If it is lying outside flange, then that is not advisable. You will not be able to use this formula. Okay. So since my neutral axis is lying within flange, I can use this. And I said that instead of here whatever B is there, you have to use effective width of flange. So based on this, what you did, you had computed percentage tension reinforcement, and so please check this calculation. I had got this as answer 0.152%. Okay, now there is always confusion like percentage PT, whether 100 AST BWD I should take or width of flange BF by D I should take. Now since I'm using here width or effective width of flange BFD, so here percentage tension reinforcement is also 100 AST effective width of flange BF by D. Okay. Why it is so? Let me show you how exactly this formula had come. It is actually coming from, so it is coming from this formula actually. Can you see here this term ASTBD? Okay, can you see this term ASTBD? So you can apply this formula since XU is less than depth of flange. So you substitute mu equal to mu max and solve this, and from here you can get what is your reinforcement. You'll get a quadratic equation. But if you can do some adjustment, I will do this adjustment you see here. What it will be done, mu equal to 0.87 Fy AST. I'll do divide by BD, multiply by BD. So here you can see D, so I'll write here BD square, and again 1 minus AST BD Fy by XV. Now this term AST by BD, I will use reinforcement ratio. So I'm using this term rho, which is reinforcement ratio. This is not a percentage reinforcement, it is reinforcement ratio. So if you do this, you will get this expression as mu equal to 0.87 Fy rho 1 minus rho Fy FCK. So this is going to give you a quadratic equation. And of course, here you can bring your BD square downward. This BD square I have brought downward. Okay. So if you solve this, what you are going to get? You are going to get a quadratic equation. It will be in this form: 0.87 Fy by FCK into Fy rho square. All right, and then you are going to have minus 0.87 Fy rho, okay, plus mu by BD square equal to 0. So you are going to get, since this is a quadratic equation, so you will get rho. Okay, so whatever rho you are getting, you multiply this 100 AST BD with everything, whatever solution you get. So this 100 AST BD, you can write this as the percentage tension reinforcement. And once you substitute everything, you are going to end up with this formula. Okay. Now, when I use this formula, as I said that whatever B is there, you are going to substitute with effective width of flange. So here it will be effective width of flange, effective width of flange. So obviously, when I'm using 100 AST by BD, here you are having effective width of flange. So that is why when you are using this formula, it will be 100 AST effective width of flange D. So this is the thing which you have to see. So you're getting 0.152%. So I'll right now not compare with minimum steel. Okay, so minimum percentage steel, I know it is how much? 0.24% for my Fe415 steel. Rather than I'll compute my steel first, and then I will compute minimum steel. Okay, so if I do this, I'm going to do 0.152 by 100 into effective width of flange 1950 into effective depth, which is 540. Now tell me how much is the answer?
1600.56.
1600.56 meters square. Now I should make sure that this AST, okay, it has to be greater than equal to AST minimum. Because I cannot compare. Here you see I have 100 AST BF by D, and whatever percentage tension reinforcement here you see, I have written 100 AST BD. What exactly B is there? So there is a confusion whether to write effective width of flange or the web width. So for that clarification, I will show you the code. It has been mentioned when you compute minimum tension reinforcement, your B has to be width of web. Let me show you that. AS by BD, what is B? Breadth of the beam or breadth of the web. So it clearly means when I'm computing minimum tension reinforcement, whatever B I'm going to give, I have to substitute width of web. So in that line, I'll compute minimum steel. So I have no minimum percentage tension reinforcement for Fe415 steel is 0.2%. Okay, so I can write AST minimum equal to 0.2 divided by 100 into width of web into effective depth. Okay, so or if you are not very much comfortable with this 0.2%, you can write like this also, or AST min by BWD equal to 0.85 by F. So either way you can use. Okay, or you use this. This is coming from code, and a little bit modification I have done for Fe415 steel. I know it is 0.2% of the cross section area. So cross section area I'm taking BW into in that fashion also you can do. So how much is AST minimum now? Can you tell me? Width of web is 230 mm. And effective depth D was, I guess, 540.
248.4.
248.4 millimeters square. So what you can observe, whatever steel you require is greater than AST. Suppose if this AST would have come less than 248.4 millimeters square, in that case, you have to provide 248.4 millimeters square. Say this calculation, whatever I'm doing, here you required 1600.56 millimeter square steel. Say this calculation gave you 160 millimeter square steel. Now you can clearly see that this steel is actually less than minimum steel. So I cannot provide 160 millimeter square. Okay, I have to provide how much? Minimum steel, which is 248.4 millimeters square. So this provision is given in the code to ensure minimum ductility in your reinforced concrete beam. So I should not worry. I am providing steel more than AST minimum. So your steel quantity is going to be what? 1600.56 millimeters square. Now can you tell me how many number of bars you are going to provide? So you said that you will be going with 20 mm diameter. When we computed this effective depth D, we said that you will be providing what? 20 mm bar. So what will be the number of bars? So it will become 6. Okay, it has to be a whole number. Okay, because it will come something 5 point something. The number of bar has to be a whole number. So you will say provide 6 numbers of 20 dia bars as flexural reinforcement. Okay, so this is how you can do it. But now thing is how you are going to arrange it. So I need to give the schematic sketch. I need to make sure whether I would be able to provide 6 number of bars in one layer. You will not be able to provide 6 number of bar in one layer. So you have to provide 3 number of bars in 2 layers. Please note, if you provide 6 number of bars in one layer, the spacing, the horizontal spacing between this bar is going to be very less, and minimum you know how much it is. Okay, it is either diameter of the bar or maximum of the diameter of the bar, comma nominal size of the aggregate plus 5 mm clearance. So it comes out as 25 mm because nominal size of the aggregate is 20 mm. So 20 plus 5, 25. So if you provide 6 bars in one layer, then that horizontal spacing between these bars is going to be very less, which is not actually recommended. So you are going to provide 6 number or 20 dia bar as flexural reinforcement in 2 layers. So I hope it is understood why I am going with this 2 layers, just to ascertain the horizontal spacing requirement is satisfied. So the structural reinforcement thing is done. If there is any question you can ask, else I'll move to the next part of this question. Do you have any question regarding this problem? So if there is any question, I would like to clarify. Otherwise, I'll move to the next part of this question.
So why we need to calculate reinforcement ratio?
Now here you see, I have this reinforcement ratio, and finally I'm making this as my percentage tension reinforcement. Now I can quickly compute my percentage tension reinforcement based on mu by bd square. I'll show you how I can do that. You please compute mu by bd square. How much it is coming? Without solving quadratic equation, without doing this thing. Once I get this mu value, and if it is ascertained mu is less than mu lim, I would be able to compute percentage tension reinforcement very quickly. What I request you is to compute mu by bfd square. How much it is coming? Can you tell me?
0.53.
Okay, so remember it is 0.53. Okay, and let me open SP16, which you will be using. This code you are going to use when we design column subjected to biaxial movement and uniaxial movement, or for designing a slender column. There you will be using this SP16. Okay, so here we have this SP16. So I'm talking about flexural member. So I'll click flexural member. And since I'm very much a little bit familiar with this, so directly I'll go to table number 2. And if you want, you can spend some time. This will speed up your calculation. So this is my table 2. What is the grade of concrete I'm using for designing the beam? M20 grade concrete, is it not? It was M20 grade concrete. FCK is M20. And what is the grade of steel? It is 415. So you see, how much was mu by bd square? 0.5. How much it was?
0.53.
Okay, I can say 0.55. Let us say you see 0.55. You see the reinforcement, percentage tension reinforcement, 0.158. And how much you have got? You have got that only, close to that. You see, you have got 0.152. See. So just by computing this ratio mu by bd square, and if I use SP16, if I know how to use SP16, I can go to some table, I can arrive into this quantity. So that is why that concept of percentage tension reinforcement has come. Here you see reinforcement percentage, PT, or singly reinforced section. Since I am having singly reinforced section, I am using this table number 2, and if I am using this M20 grade concrete. Suppose if your grade of concrete changes, you go to next table, you see M25. Say if you wanted to know, like say if you are using M25 grade concrete, what will be my percentage tension reinforcement? You see it is for 0.55, it is 0.156. And this percentage tension reinforcement is also very useful when you compute the shear strength of the concrete. So that is why I thought of introducing this percent tension reinforcement, and you have to, as I said, how exactly it has come. I've given you the basic by introducing this reinforcement ratio and little bit modifying this reinforcement ratio by multiplying 100. I'm saying this is my percentage tension. Is this clear?
Yes, sir.
Okay. So if there are any other question, I would like to clarify, else I'll move to the other part of this question. So the other part of the question, I assume that there is again no doubt. You have to determine the location where 30% to 50% reinforcement can be theoretically curtailed. Now, why you need to curtail the bar? So to understand the curtailment of the bar, let me draw the line diagram for the beam. Here you have this ultimate load. Now corresponding to this ultimate load, this is the bending moment diagram, which is positive bending. It means that you're going to provide reinforcement on the bottom fiber. Okay, tension is in the bottom fiber. So this is what you mean by positive bending moment. And if you have negative bending moment, it means the tension is in the top fiber. You have to provide reinforcement on the top. Now you please understand, here you have this maximum moment. If I move beyond this point, like suppose if I talk about this particular point, at this particular point, I have the moment quantity. So this is my section 1-1. So at section 1-1, I have this moment M1. Now this M1 is less than M max. So why I need to provide 6 number of bars at this particular section? So please try to understand this. 6 number of bars is required where? It is required at mid span, because there I'm getting maximum movement. But as I move away from the mid span, I can see there is a reduction in my movement, and as I come near support, my moment is actually reducing. Many times what you will find, say this is your beam, this is your beam, and what I'll be doing, I'll be placing my reinforcement. So say you have a 6 number of bars, which is required actually at mid span. So what I'll be doing, say you see, this is 1 bar. Okay, so let me draw parallelly the cross section also. So this is the section at XX, okay, at mid span, and YY. So you see I have placed 1 bar, say this bar is, let me make this as my section XX, and this is my section YY. So I have placed 1 bar, so 1 bar, say it is here, so same bar I can see here. So again I am placing 1 more bar, because this is in the front view which I am showing you. So I have placed over here. Again I am placing 1 more bar. I am placing, you see 3 bars have been placed. Now more 3 bars have to be placed. So this time what I will be doing, I am curtailing the bar. So please see, this is the bar which I am providing. I have curtailed the bar. I am not providing this bar throughout the length of the beam. I have curtailed. So I need to specify at what length I should curtail the bar. So curtailment means cutting the length of the bar. So you see in section YY, I cannot see this bar. So I will not be able to see that bar. But at section XX, that bar is going to be visible. Similarly, 4th bar I'm going to place, 5th bar I'm going to place over here, and 6th bar I'm going to place. So observe section XX and Y section YY. In section XX, at midspan, you can see 6 number of bars, but near support, if I cut a section YY, I see 3 number of bars. Why I have done that? Because near support, my moment is less. Now, if my moment is less, my 3 number of bars which I am providing. So here you see whatever 3 number of bars which I provide, this is going to give me my moment of resistance more than whatever is the moment which is going to come over here. Is this point clear to everyone? Why we are curtailing the bar? Curtailment of the bar is just to done so as to achieve economy in terms of saving your reinforcement quantity. So here in this question, it has been asked theoretically, and later we will see actually theoretically whatever point we get, there we do not curtail it. We extend it by some length, and this topic we'll be discussing when we discuss the topic on development length. But right now I want to introduce this. I would like to know theoretically where you should curtail, okay, or determine the location where 30% to 50% reinforcement can be theoretically curtailed. So let me come to the sketch. You have 6 number of bars. Okay, if you have 6 number of bars, if I say if 3 bars are curtailed, if three bars are curtailed, what it means, you will say that it is 50% curtailment. 3 divided by 6 into 100, so you'll say it is 50% curtailment. And if you say if 2 bars are curtailed, how much percentage curtailment it will be? Any one of you?
33%,
right? It is coming 2 by 6 into 100. So if you are curtailing 2 number of bars, it means 33%. So in the question it has been asked that what should be the point where you should actually theoretically curtail, okay, where at what point you should theoretically curtail such that there is 30 to 50% curtailment. So you can curtail either 3 number of bars or you can curtail 2 number of bars. So it is up to you. So what I'm doing, let 2 bars, or let me use 3 bars itself for change. let 3 bars from. So please see, you have this reinforcement in 2 layers. Okay, you had reinforcement in 2 layers at mid span. So I would like to remove this one of this layer. This layer I would like to remove as soon as I come near support. So that is why I'm saying let us remove 3 bars. Okay, so I'm writing let 3 bars of 3 bars from second layer curtailed. So if you remove this 3 number of bars, so what is AST of remaining bars? So what will be AST? So what will be AST say at section YY? So we have a curtailed the bar. So what will be AST at YY? So it will be 3 into 5 by 4 into 20 square, or 3 into 314. How much is coming?
942.48.
942.5 millimeters square. Okay, so this is what you are getting, 942.5 millimeters square. Now what I will do, I'll compute what is the moment of resistance at this particular point. Okay, or I am asking you, what is the moment of resistance when you are having only 3 bars? So can you compute what is the moment of resistance? Moment of resistance of this section. So in fact, you have to think the problem like this. Instead of 6 bars, you have 3 bars. You know the width of web, which is 230. You know what is depth of flange, which is 120, and the overall depth was 570. So can you compute moment of resistance of this section? So we already know your neutral axis is going to lie within flange. So I can compute the moment of resistance. So what will be the moment of resistance? Or what you do? You make this sketch. The neutral axis is, you're confirmed, the neutral axis is lying within flange. Okay, so you can draw the stress block diagram. So here you have this tension force. Okay, here you have this compression force. This is your lever arm. Okay, this is your lever arm. So I recommend you compute the value of XU and compute what will be your moment of resistance. Can you tell me what is the moment of resistance? You can apply this formula also directly. Since your neutral axis is lying within flange, you use this formula to compute moment of resistance very quickly. So if you use this formula, how much is the answer? So mu equal to 0.87 into 415 into the AST. AST was 942.5. 942.5. Effective depth D is 5. How much it was? 540, right? 540 into 1 minus 942.5 into 415 divided by B will be effective width of flange. So it was
180.34 kilonewton meter.
How much it is coming?
180.34.
180.34 kilonewton. So others please check this. 180.34. Others also please check. Are you getting moment of resistance as 180.34? So if you're getting 180.34, let me come to the bending moment diagram. So you see here it is, I'm cutting the bar. So here in the bending moment diagram, whatever moment I should have, this mu should be equal to what? Moment of resistance. So that is what it is saying. If my moment of resistance is equal to my applied moment, then my beam is actually safe. So that is the actual theoretical cutoff point. So I'll say let x be the distance from support where curtailment is done. So I would like to say that at distance x, I am curtailing. So I would like to know what is my moment at this section. Okay, what is the moment at this section? The moment at this section is going to be what? This reaction Vu into x. Okay, Vu into x minus W into x square by 2. So what is going to be my moment at that section? Moment at this point, right, mx equal to the reaction is shear force, so I'll write vu into x minus wu into x square by 2. We had computed the reaction was your shear force. How much was this? It is 201 kilonewton, as you can see. 201 kilonewton into x minus W. What is the ultimate load? We had done this calculation. The ultimate load was 67 kilonewtons per meter. So this was the ultimate load. Okay, 67 minus 67 into x square by 2. Now this moment has to be equal to what? The moment at the curtailed point, because at that point you would like to curtail. So here it will be 180.34. You have to be very careful with the units. Here I am using kilonewton meter. My reaction is also in kilonewton. My load is also in terms of kilonewton per meter. So whatever x you are going to get, this will be in meters. So now tell me how much you solve this quadratic equation and tell me how much is your x.
Sir, 1.90 and 4.90.
1.90 and?
Sorry, sir. 1.09 and 4.9.
Okay. 1.09, so let me write down 1.1 and 4.9.
4.9.
Okay, so how you are going to interpret this? Please see over here. I am curtailing this at 1.1 meter. Okay, another what I am doing, I am curtailing at 4.9 meter. And you see 4.9 plus 1.1. How much it is coming? It is coming 6 meters. Is it not? So I can write this as theoretical point of cutoff for 3 number of 20 dia bar is 1.1 meter from either supports. So this I can write. From either support, what I will be doing, so from here I'll be taking 1.1 meter and I'll cut the bar, and from the support I'm going to again take 1.1 meter and I'll cut the bar. So this is my theoretical cutoff point. Okay, but please understand, actually we do not curtail our bar at theoretical cutoff point. Okay, so you please make this note that this is not the actual point of cutoff. And we'll see this, okay, because there is a provision in the code, so we should understand first development length, and once we know about development length, then what we do, we actually extend by certain length from the theoretical cutoff point. Then we decide where exactly you should finally curtail your bar. Okay. So I hope this problem is clear, and if you have any question you can ask, else I'll end this session. And again, one more class I'll be taking for doubly reinforced flange section, and I will start with the problem itself. So if there are any questions pertaining to this problem, you may ask, else I'll end the session. Anything? So if there are no questions, then I have to assume that there are no doubts.